All right. Welcome to Equilibrium Part 208. Of course, a slight exaggeration there, but it's pretty much accurate, right? We're just never going to end equilibrium. I just wanted to start off, let's do a couple of problems, and then we'll start talking about titrations today. So let's say that I want a buffer of pH 5 using, let's see, which acid or base shall we use? Let's see, how about we use, let's use benzoic acid. And sodium benzoate. So if Ka for benzoic acid is, what is it going to be? Where did it go? 6.46 times 10 to the negative 5. So using let's say 2 liters of 0.1 molar benzoic acid how many grams of sodium benzoate do I need to add? And let's assume that we don't have any volume change with this. Sodium benzoate would be C7H5O2Na, I guess we'll put up there. That would technically be the formula for sodium benzoate. So we'll leave that alone though. So, what the heck are we going to do here? Hi, little dude. You have to go on the couch now. All right. So I want a buffer of pH 5 using benzoic acid and sodium benzoate. We're given the Ka of benzoic acid, and we're given that our concentration of benzoic acid should be 0.1 molar. And we're... Oh, cute. He's playing with the toy. He's never done that before. So we're asked how much sodium benzoate to add. So this is a buffer solution, right? So chances are we should probably use the Henderson-Hasselbalch equation as is written there. We know that we want our pH to be 5.0. We know that our pKa would be 10 to the... no, it would be negative log of whatever this was, 6.46 times 10 to the negative 5. Or if we just look on our chart, because the pKa is given there also, we would see that the pKa is 4.19. Either way. And we know that we have our concentration of HA, our benzoic acid, and we're trying to figure out the concentration of A minus, right? So we know therefore that 0.81 will equal the log A minus log of 0.1. So let's go ahead and figure out what the log of 0.1 is. Where is Google? Log 0. Oh, wait. How do I not know this? It's -1. Duh. I don't know why I needed a calculator for that. So remember log of 0.1 would be -1. It's 10 to the power of whatever gives you 0.1. So if it's -1, that means log A will need to be -0.19. And therefore A will be 10 to the power of 0.19, which we can go ahead and solve. That one I can't do in my head. 10 to the -0.19 is 0.645654. Fun number there. Concentration would be molar. With all this stuff, it looks like we're probably going to have 3 sig figs. So let's just keep that in mind as well. This should be A-, by the way. And so, if we want to find the mass of it, well, we know what concentration we need. So we need this concentration. And so we have enough information in the problem to figure out the rest of it. So again, we're assuming no volume change. So we know that we're going to still have 2 liters of solution that we're working with, which means we can therefore use concentration to get moles, and from moles we can get mass, as always. So let's go ahead and do that. We have 2 liters will equal moles, and so if we go ahead and, oh my gosh, I'll write out our units here. The molar mass we could find, for me, I will go to Wikipedia and do it. Sodium benzoate. Sodium benzoate's molecular mass is 144.1. And so doing all this fun stuff. I don't know why I keep closing Google, because I very clearly need it for my math, but let's go ahead and do that. Okay. I don't even know where my cursor went. There it is. Okay. So 0.645654 times 2 times 2 divided, or times 144.1. We do all this stuff. We end up needing 186 grams of sodium benzoate. All right, so if we were asked to figure out how much of something we would need, this is one way we could do it. So using the Henderson-Hasselbalch equation, we can figure out the concentration of the base we need, or the acid, depending what you're given in the problem. And you can therefore, once you have your concentration, you could figure out its mass, depending on your volume. So in this particular one, we ended up with 186 grams. It's quite a bit, but lo and behold, we have made our fancy buffer, and we've made a lot of it. So 2 liters, quite a bit. So cool. Any questions on that one? All right. I want to do one more. This time it's going to be not a homework problem, but it is one from your book that I think we should do. Which one was it? Yeah, let's do this one. So we have 10 grams of ammonium chloride and 250 mLs of 1 molar ammonia. Let's find the pH. Actually, let's just find the pH. Let's just do that. So, go away book. All right, let's go ahead and see what this one's going to be. So, we're kind of just working in reverse here. Sorry for forgetting the unit. So, notice here we have ammonium chloride is NH4Cl, which is an acidic salt, right? And of course, ammonia is a base. So we can use the concentration of ammonium ions as HA, and then the concentration of ammonia would be A minus. So remember, the charge doesn't necessarily have to be the same thing here. Just one of them is got one more proton and it's more positive, right? So we can use those for this particular one. So with that in mind, let's go ahead and work with this. So if we have 10 grams of ammonium chloride, we need it in concentration, right? So we're going to need moles for this. So we're going to want to use our molar mass. Let's go ahead and look it up. NH4Cl. Molar mass is 53.49. Oops. And once we have moles, we can divide all of this by 0.25 liters to get our concentration. Remember, this is a strong electrolyte, so it will completely break apart into ammonium and chloride ions. All ammonium things are soluble, right? So we're good here. Let's go ahead and do this. So 10 grams divided by 53.49 divided by 0.25. We end up getting that the concentration of ammonium ions is 0.7478, 3 sig figs there, molar. And so if we're figuring out what the pH is, we can go ahead and use the Henderson-Hasselbalch equation. And for us this time, that will be pKa plus log of ammonia over ammonium. And so we're going to need the pKa of the ammonium ion. So let's go ahead and look that up on our chart. The ammonium ion has a pKa of 9.25. We had 1 for our ammonia, and then we just calculated the ammonium to be 747. Little dude, you've got to play with your toy or something. So we can go ahead and just calculate this now. So 9.25 plus log of 1 divided by 0.7. 7478. Doing this, we get 9.37. Let's say 38. Cool, yeah. That would be our pH here. And let's just think about this. Does this make sense? This pH is slightly more than the pKa. Right? And so that means that we should have slightly more base than acid. And indeed we do. We see that we have a higher concentration of our base than we do our acid. So this number makes sense. So we're good with it. That should be our answer there. All right. Any questions on that one? Oh, relax, dudes. Just so we know, well, I didn't necessarily go over this yesterday, the Henderson-Hasselbalch equation really works best for solutions where your concentration of acid and base are much greater than your Ka. So typically that's going to be an important part for this particular equation. It's an important assumption we make. If you end up having very small concentrations of acid and base in there, it becomes less valid. You may have to use an ice table instead. Because we're with this, remember, we're making that assumption that the Ka is much smaller, so that our X is going to be much smaller in comparison. So just let that be in your mind. Typically for this class, we're going to be dealing with stuff with particularly large concentrations, so we'll be able to use the Henderson-Hasselbalch equation. But if we wanted to do it a different way, we could. We could do an ice table and do all that fun math and quadratic equation and blah, blah, blah. Alrighty. So, let's just do one more practice bit. Let's say we add... How much do we want to add? How much do we have here? 250 mLs? Okay, let's add 25 mLs of some HCl to this. Let's see what's going to happen here. Let's see what's going to happen to our equilibrium if we do this. Let's see what the new pH is going to be. So again, we're going to be able to use the Henderson-Hasselbalch equation. Yesterday when we did something like this, when we saw the pH effect with a buffer system, we did an ice table, but we don't actually have to do an ice table for this because we saw yesterday that all of the acid is going to react, right? And so we can actually just use our stoichiometry knowledge instead. We don't even have to worry about an ice table. So we can just use the number of moles directly. So if we see that this is going to be 0.025 moles of H plus that we're throwing into our reaction here, we know that that's going to react with ammonia, right? It's going to react with the base. In this case, that's the ammonia. So if we want to see how much ammonia we have in this whole nonsense, well, it looks like we have 0.25 moles of ammonia, right? Stoichiometry, if we really wanted, we would throw out an equation. Something like that. We would see the coefficients are 1. Technically, we would do our... we would see how much ammonia is used up, or if we were just wise about it, we would just subtract the 2. Which means that we have 0.225 moles of ammonia left. And now we have added some moles of ammonium to this. Hopefully nothing too crazy here. It's just simple stoichiometry. If you really wanted to do the whole dimensional analysis, you're more than welcome to. You could see how much ammonium you would get. And you would also be able to see how much ammonia you have left. That would all work out. And so, with that in mind, now we can go ahead and figure out our concentrations. So if we have 0.225 moles of ammonia over our total volume, note that this volume is, oh my goodness, that's going to be the 250 plus 25 mLs. That's the total volume there. We end up getting 0.225 divided by 0.275 0.81818 molar of ammonia. And so now we just need to go ahead and add our ammonium to our previous one. While we necessarily didn't stop at moles for ammonia, we technically did that. We know how many moles we had to begin with. So it was 10 divided by 53.49. So for ammonium, we had 0.1869, 5 moles. Now we're adding 0.025. So that'll be 0.21195 moles. And if we want to go concentration, we have to also divide that by our volume. And so doing so, we get 0.7707 molar. Now we can go ahead and throw in our Henderson-Hasselbalch equation. So the pH will be 9.25, pKa same from before, plus log of 0.8181 over 0.7707. Do this. 9.25 plus log 0.8181 divided by 0.7707. Do that, we get 9.27. So we have, actually 0.28, I guess. We have very slightly decreased our pH after dumping in that whole bunch of acid. So again, we've already seen that buffers don't really change their pH very drastically. That's the whole point. If we just wanted to kind of check again, we are adding acid, so we are expecting the pH to go down a little bit. Notice that what we started with before, the ratio was 1 to 0.74. Now we have 0.81 to 0.77. So we have kind of brought those two closer together. So we've used up some of our base. We've made some acid as a result. So there we have it. Alrighty. Any questions on that? Alrighty. If there are no questions, then let's actually now talk about titrations. So titrations are technically just a means of adding an exact volume to determine how much volume is needed to react. For that, we use a whole bunch of different things. Typically, we use acid-base chemistry or redox chemistry. These are typically things that are done using volumetric analysis. So we have a burette, which is a device that usually could measure. It usually is accurate to 0.01 mLs. So again, we're getting pretty exact volumes here. You can add things dropwise to some solution of something you're analyzing. It's the process of kind of controlling how much of that solution you add to your mixture to wait for some reaction to happen. Usually you have some sort of indicator in here to let you know when the reaction is done. That could be a pH indicator, or it could be a redox indicator. These are both kind of pretty common ways of doing titrations. So when you get pulled over for drunk driving, which you should never do, don't ever do that, they will test your blood's alcohol level by doing a redox titration with it. They'll basically put in some either chromate or dichromate to oxidize the ethanol in your blood, and they'll see how much of that is going to happen using a redox titration for the color change there. Generally, in chemistry labs in high school and what are you doing, Miss Jersey? Get out of there. Or in college, we do a lot of acid-base titrations as well, which is kind of going to be our focus in class today. We'll be on acid-base titrations. So you do have a lab sim, so you will be kind of doing a titration yourself, or at least seeing how it kind of all works this week. But let's go ahead and look at things as a titration happens. So a titration involves adding a base to an acid or vice versa. Typically we do add base to acid, though. That's just pretty common, but you could do it the other way around. And if we want to take a look at graphically how this would look, if we have pH and then the moles of, let's just say milliliters of some base, we'll say sodium hydroxide. We typically use strong bases for titrations. If we have a strong acid in here, we're going to see that the pH versus the amount of base added graph will look somewhat like this, where we're going to start with something, pretty low pH, and we're going to end with something pretty high pH at the end of it. So this is what's going to happen as we're adding base slowly to this particular acid. And we're going to see that once we've added an equivalent amount of base to our acid, we have what is called the equivalence point. And that's going to tell us when moles of acid equals moles of base. That is what we're going to define the equivalence point as. And so there's a couple of things we can see about this particular graph that are of interest to us. Notice we start with a very low pH before we add any base there. And the pH very slowly rises for a while. And then we have this very sharp pH incline. So we're adding our base. Once we have almost all the acid gone, we start shooting up in our pH. Just like one drop can take you from pH 3 to pH 8. That's as much as it takes when you're using a strong base sometimes. So that's what we see, this very sharp, almost vertical area in our graph here. That's right in the middle. We see that the pH of equivalence is about 7. If we're using a strong acid, strong base, we don't have any weak acids, weak bases in here. We're expecting if we put equal amounts, they should just neutralize each other. We'll end up with a salty water, and that's it. No, where it's going to be fairly neutral. All right, and then at the end, we end up again with we end up at very high pH with this. So this is characteristic of reacting a strong acid with a strong base. So we see, again, looking at our graph here, slow increase, very, very sharp curve, equivalence point around 7, and then it kind of is just symmetrical on the other side where we go through. If we look at a weak acid, however, if we look at how about using a weak acid plus a strong base, we're going to see that we have a couple of different key factors here. If we do the same kind of graph here, I'll try and make this, you know what, let's not even worry about starting that low. Whatever, good enough. Looking at this, we'll probably start maybe here or so. And actually, hold on, I did that kind of poorly, but that's kind of what the graph is going to look like. Notice a couple of things about this. Our equivalence point, roughly there, kind of the inflection point of this graph, is going to be a bit higher than pH 7. And let's look at that, and let's look at why. The pH at equivalence is greater than 7. Often it'll be 8, 9, 10, somewhere around there. All right, and so the reason for this is, if you look at what's happening with this, this is the reaction that we're kind of undergoing here. Since if this is a weak acid, that means that this is a weak base. And so after we have reacted these two, if we have completely reacted all of our acid and all of our sodium hydroxide, we're left with a solution of weak base and water. And as a result, that will raise the pH. So once you're at equivalence, once you've added equal amounts of acid and base, you end up with a basic solution because you have that weak conjugate base still in there that's able to react with water to raise your pH. And so that's why in this graph we see, in this particular example, we see that the equivalence point pH is somewhere around 8.5 or something. Just making up the graph, but definitely is bigger than 7 because we're left with a solution of weak base afterwards. So once all the weak acid, so at equivalence, at the equivalence point, once those guys are equal, they kind of cancel out. And so we only have A minus and water. And so as a result, that A minus can react as a weak base, and so we end up with a basic solution at the equivalence point. All right, hopefully that makes sense. So we will have used up all our acid, all of our strong bases used up at the equivalence point, they're the same. So we're left with A minus and H2O. The reason for this is neutralization reactions, by the way. Have very high equilibrium constants. So the equilibrium constant of this is, oops, I guess putting it to water. We know this, right? We know that this is going to be 10 to the 14th. Very, very big K, right? It's the opposite of our ionization of water. So 10 to the positive 14 is a very, very product favoring reaction. So we don't really need to worry about kind of other effects happening here. So the neutralization will always take place. We're not going to have to worry about the ionization of the acid or anything like that, or anything similar, because the Kc for neutralization is very, very high. Very, very product favored. So we're going to just react that H plus as soon as it goes in there. So we don't even have to worry about an equilibrium or anything with this. We can just use pure stoichiometry. Alright. However, once we're done, once we're at the equivalence points, that's when we have to worry about using our equilibrium stuff. So we can use our Henderson-Hasselbalch or whatever there. Alrighty. So with that in mind, a couple of other interesting points are on this. So if it took maybe 25 ml to react this, at 12.5 ml, we have, this is, by the way, the equivalence point. This one is called the half equivalence point, where we'll add half as much NaOH as we need. And what that means is that we will have reacted half of our acid. If we've reacted half of our acid, that means now we have the concentration of acid and its conjugate base are equal. If we've reacted half of our acid, right? Now we have produced, if we had 1 mole of acid, we react half of it. We now have half of the acid left, and this now is the base. So we have reacted half of it. At the half equivalence point, the pH is equal to the pKa. So that's another important facet of a weak acid titration, is learning that at the half equivalence point, your pH and your pKa are identical. Because remember that Henderson-Hasselbalch gives us this thing. Remember that the log of 1 over 1 is 0. So that just goes away. And so we're left with just pH is pKa. So that's at the half equivalence point. So another important figure to add in there. We'll do some math of these titrations in a little bit. But just one more thing to look at here is that also in a weak acid titration, we're going to see that the pH is, relatively speaking, higher than as if we were using a strong acid. So your initial pH, maybe we started with about 4 or 5 here. If we go way back, we started with a pH of 1 or 2 in our strong acid one. So you can tell these two apart by not only looking at where the equivalence point is, but also kind of where you're starting. A strong acid will have you starting at very low pHs. Weak acids will have you kind of starting at higher pHs. Alrighty. Any questions so far? All right, let's do one more graph here. Just comparing some weak acid stuff. Same graph. We're going to see that we can have, oh no, the same graph happening with different acids. And what, God, these are just terrible, but let's say that the pKa of this one is 8, pKa is 6, pKa is 4. Notice some interesting things about these. Your equivalence point will increase as your pKa increases. And that makes sense, right? A high pKa means a weaker acid. A weaker acid means a stronger conjugate base. And so we're going to expect our pH to increase once we have that conjugate base in solution. We're going to see that, of course, as a weaker acid, you're going to end up starting with a higher pH than you would with a stronger acid. And so, of course, your half equivalence point, which is equal to the pKa, of course, will also be lower, right? That would be 4. That would be 6. That would be 8 on our pH graph here. And so that's kind of the trend that we're going to see here. So we're going to see that the equivalence point pH will increase as your pKa increases, because the weaker acid means stronger A-. Remember, they're inversely related to each other. So the weaker your acid is, the higher its pKa is. That means we're going to have a stronger A- in our solution at the equivalence point, so our pH will go up as well. All right, so if we're just comparing different ones, we're going to see that stronger acids will have lower pHs at equivalence point. Weaker acids are going to have higher pHs at the equivalence point. All right, so hopefully nothing too crazy there. Shall we do a problem? So let's see, what is the pH of a solution after 45 mils of sodium hydroxide is added to, there, let's even be more good with our sig figs. What acid shall we use? How about formic acid? Which is going to be that guy. Let's go ahead and see what the heck this is going to mean. So formic acid, we know, is going to react with sodium hydroxide. We're going to end up using up all of our sodium hydroxide. Oh, I guess we should have the concentration of formic acid, huh? Let's have it be the same concentration. So with this, we're going to be able to figure out the pH of the solution by taking a look at some of these numbers. So we know that we have, what are we having here? We have sodium hydroxide plus formic acid. Actually, it's not even going to be equilibrium. We're going to make water plus sodium formate. We know that we are starting with 45 ml. We have 0.1 molar. We have 0.1 molar here and 50 ml. We know we're going to use up all of our sodium hydroxide. We can tell right away that's limiting, right? We have obviously less than that. And this is going to be a stoichiometric, calculation. So we know we have to use up all the NaOH. So if we go ahead and see how many moles that's going to be, that's going to be 0.1 molar times 0.045 liters. I don't need a calculator to do this. It's only 3 sig figs now. All right, so that's how much NaOH we're going to be using in this reaction. Which means we're going to be using up that many moles of formic acid as well, right? The ratio is 1-to-1 from our stoichiometry, from our chemical reaction here. So for the formic acid, same calculation here. So if we're going to be using up that much base to use up that acid, we're going to end up with... Did I forget some zeros? I did, sorry. So we're going to end up with small concentration left of our acid. And we know that all of that moles of acid that we used up is now our... That's going to be the same amount of our conjugate base left. Right? We will have used up some of our acid, and whatever's left now stays as acid, and whatever reacted now becomes conjugate base. We can try the Henderson-Hasselbalch equation here. These are probably concentrated enough where we can make this work. Though maybe it's a good exercise to just compare. We can try doing the ice table as well. We'll see what we get. So if we do this, Henderson-Hasselbalch equation, formic acid, let's go ahead and look it up on our chart. Formic acid is a pKa of 3.75. So these, probably Henderson-Hasselbalch is not the best idea to use here, but we'll just do it anyway. 0.0005. Let's go ahead and do this math. All right. 3.75 plus log 0.0045 divided by 0.0005. Doing this, we end up with a pH of about 4.7. Where did I go? There we are. 4.7 or so. So we're kind of reaching at this point. We're getting close to that kind of slope where we're going to get to our equivalence point. If we wanted to figure out what it is at equivalence, we can do that as well. So this was after adding 45 mLs. If we add 50 mLs, if we have 50 mLs of our base, we will have no acid left. And now we just have our anion. We have our conjugate base only. This is all we have going on in our reaction. Sure, some sodium ions, but who cares? Those don't affect pH, so we don't need to worry about that. So with that in mind, we can figure this out as well. Wait a second. I used moles instead of concentration, didn't I? Shame on me. We should have converted these to concentration. Oh, let's do that real quick. Oh dear. So these were both over 0.95 mLs. Oh my goodness. All right, let me fix that. Let's see if this changes our pH. 0.95. Oops. You do get the same answer? Okay, yeah, it makes sense, right? Because they would both be divided by the same thing. So, but we should be good scientists and have everything correct there. So we should be good. All right, and let me just put more parentheses. And yes, we do get the same answer. So good. But technically, we should use molarity, not moles, Just make sure you keep that in mind. Okay, sorry, back we were. So in our solution of 95 mLs, we now have a concentration of 0.005 divided by 0.095. We have this many moles, or molar formate. And it looks like it's going to be time for an ice table. We love our ice tables, don't we? We know that formate being a base, will react with water to produce OH minus and the formic acid. So we're looking at a KB here. We know we have this. We have nothing of the other two. So, as always, we do all this fun stuff. This is, of course, an ice table. I don't know how to spell ice. So we get x squared over 0.5263 minus x equals kb, which is going to be, oh my goodness, that'll be what? 10 to the negative 10.25. Remember that pKa plus pKb is 14, so if we had 3.75, our pKb is 10 to the 10.25. So all this stuff should be there. Definitely our KB is much, much smaller. Our X is going to be very small compared to the KB value here. So we can make our assumption. If we do this, X is going to be equal to 10.25. Screwed that thing. It's going to be such a small concentration. 0.000. Oh my god, how many? So 7.49 times 10 to the negative 6, I think. Molar. That's going to be our hydroxide concentration. So our POH will be negative log of that. So let's do that. Log of the answer. So the POH is 5.125, which means that the pH is going to be 14 minus 5.125, which will be equal to 8.75, and I think we need to round this to about 8.88 or so. So this would be the pH at the equivalence point for this particular acid. So we're going to have that there for this particular solution. So this stuff gets complicated. Gets complicated once we throw more stuff in here. So our ice tables will still be here. They're always going to be part of our calculations. But that's how you would calculate the concentration at the equivalence point. It's just now throwing in some stoichiometry to our ice table stuff that we've talked about before. All right, questions on that one? Alrighty. If we want to just throw in at the end here a polyprotic weak acid, we're going to see that the graph is just going to look like as if we took two graphs of two weak acids and just smushed them together. We're going to see that that graph is going to look something like this, where we're going to end up having 2 points here. if it's this is a diprotic acid. So some diprotic acid, whatever it happens to be. Again, this is our milliliters of NaOH added. This is our pH. We're going to see that we're going to have the same kind of points here as we did before. Once we've added kind of one molar equivalent of our base to our acid, we're going to be looking at where the pH will be equal to the pK or the combined pK. Okay, let's just, let me slow down. Let's look at these individually. Okay. So this is going to be the kind of second equivalence point over here. We have our first equivalence point here. We have our first half point there. And I'm totally out of room, but our second half equivalence point there. And it's going to be very much the same as stuff that we saw with monoprotic acids, except now it's just two graphs instead of one. So we're going to see that we're going to have, for a diprotic acid, we of course have pKa1 and pKa2. We're going to see at these half equivalence points, we're going to have the pH equal to those pKa's. So we can really just look at these kind of individually. So this would be pKa1. This would be pKa2 up there at those black dots at your half equivalence points for each proton. And interestingly, your first equivalence point any idea what that one is going to be? The pH of that. It's an interesting one. Though I guess we may have to get to this tomorrow, but what do we think the pH is going to be equal to there? Is there any sort of guesstimate we can do? Not quite. That would be the half equivalence point, right? At half equivalence is when we're equal to pKa1. And then at the second half equivalence point, we're equal to pKa2. We're going to see that this one is pretty much going to be the average of them. So it's going to be in between those two pKa's. It'll just be the average there. So yeah, exactly. So we're going to see that point, at that first equivalence point, we're going to have those two averaged out to give us our pH. So of course we could just calculate this all, do all these ice tables and all this fun stuff, or we could just use these easy shortcuts. So either way. So we're going to see that we can have kind of either thing happening here. And just to kind of rush through, a buffer solution, its titration will look something like this. This would be something like with a buffer. This is going to be, again, mils of NaOH added, or acid, it could be either way. This would be our pH. We're going to see, again, pKa is halfway through there. We're going to see that this whole area is going to be the buffer capacity. And that is usually pKa plus or minus 1 pH unit. So that's going to be how much your buffer will be able to kind of withstand extra base or acid being added. So that whole region, we're kind of roughly around the pKa. And within 1 pH unit of pKa, that's where we're going to be able to buffer our solution and not have that pH change very much. After we get through that one pH unit from our pKa, that's when we start going crazy again with these steep slopes. So that's what we're going to see here with a buffer as well. All right, we're out of time today. We'll just finish this stuff up tomorrow, and then we'll start talking about solubility, equilibria, and other fun stuff like that. All right, so I'll see you guys tomorrow. Enjoy your Tuesdays.